Hello, welcome to this video. We'll be going through the USACO 2016 February contest, Bronze Problem 1, which is called Milk Pails. Go ahead and you can take the time to pause and read through the question here. Okay, let's go ahead and take a look at what this is saying. So first, let's just take a look at what the input is. So the input is X, Y, and M. So those are if we take a look up here, that is the X and Y. So those are the three milk pails of size some value. So we know that X can be 1 or higher. X is always smaller than Y, and Y is always smaller than M. And M is between 1 and 1,000. But I guess if it was 1, it wouldn't be possible. So technically, M would be bounded by 3, but that would be for another time. What we know for a fact is what I guess in this case Farmer John can do is fill X until in size M pail, so from X to M, so long as M does not overflow. You can Farmer John can do the same with size Y, so fill Y and then pour it into M, so long as it doesn't overflow. And the idea is to fill the size M pail with the maximum amount, such that it doesn't overflow. What's the maximum amount that it can be had? So in this case, we're given this 17, 25, and 77. So those are the different pail sizes. And given this, so what is the maximum amount of milk that can be placed inside of size M, given the operations above? So you can either pour 17 into 77, or 25 into the 77 pail. So we know that it's going to be upper bounded by 77, so that's the maximum value you can have. And I mean, it's unlikely to be 0, but we can lower bound it by 0. Or in this case, actually, we can lower bound it by 17 in this case, because we know nothing can be less than 17, unless you have 0 pails, but that means you should be able to add at least 1. And in this case, the highest value you can get is 76, which is size 17 3 times, and size pail 25 once. So let's just take a quick illustration of what this might look like. So let's have a small pail right here, medium pail here, and then the large pail we'll say is this one. So again, the operations from above are you can place the small one here, so we'll call this small, medium, and large, or in this case, X, Y, and M. And then medium can also be placed into large. One of those two operations are possible. So in this case, one solution that you could think of is to start off basically simulating this. So start off with small, pour as much of the small in, and then try pouring the medium, or vice versa. So start with medium, start pouring it in, and then try to put in the small. Some combination of, in this case, because it's X, Y, M, we'll do some I value times X plus J times Y is, well, not necessarily equal to. It looks something like this, so less than or equal to M. And we're basically just trying to maximize this. So try to find the maximum value of I and J such that, let me maybe make that clear. So these are the levers we can control. We're trying to maximize I and J such that the whole thing, the maximum of that, should be less than or equal to M. Okay, so let's go ahead and take a look at how this could be done. So for this Python code, what I first do is read in the files, then just convert that to an int. Those are the pail sizes. Then in the solution, what I do is decompose X, Y, and M. Oops. And first what I try to do is find the max X, such that in this case, I do integer division. So M integer divide X. That gives me back, think of this as how many times can you fill just with X, the X pail? How many times can you fill that in? Same thing for y. So if you do that, so just with y, how many times can you do that? And then in this case, if max x times y, or max x times x equals m, or max y times y equals m, then we're saying that you can either fill with just the x bucket and then just pour all that in always, or with the y bucket and just pour that in always. Then the maximum value should always be m, so we just return m. Otherwise, there has to be some combination of x and y that can be much either higher or better or some way better. So first I do is I create a best value. So that is the current best at the moment. Then I go through a for loop. So for I in range 1 through maximum x plus 1. The 1 in this case is signifying that we don't need to start at 0. So we need to at least have one x value. Otherwise, max y would have been positive. Since we know that x is smaller than y, we can always place in, we can always substitute a x for a y. Okay. Then we have j. The j value here is just representing from the formula before. That's the something that you times the y value. And here we're just trying to maximize it. So starting off with I times x, and then j, we're increasing that by 1 every loop here. We do a print. You don't need this. We just print out the x and y for debugging. The best value here we define as the maximum between so the current best and the I times x plus j times y. So this is a little bit inefficient slightly, or at least not the best you can do, but it does guarantee the solution because we're going through for loops and we're just trying to somehow mix and match the values so that we get the best value. It is a little bit more efficient because of this while loop. We terminate as soon as it goes overflow, rather than if we did a for loop, then we'd have to go through all the different steps for the similar here, like 1 to max y plus 1. So this just guarantees a little bit efficiency with terminating as soon as it overflows. And once we go through the whole loop for both of them, then we return the string best, or the best value, and then convert it to a string, and then we output that to the answer. So with this, we should get, I think that's from another test case. We get that. So running this through, you should be able to, running the sample input, we will be able to get 17 to 76. Okay. Thank you for watching. Have a nice day.